Last time, it was a big lesson, right? Story time, and we're introducing all these weird new bits of notation and weird different ways, terms to describe things. One of the key things that we introduced was this idea of first principles. If you want to find the gradient function of a function, okay, we introduced this idea of rise over run, where the rise and the run get really, really, really small, okay? So, if you remember, we call that first principles, right? We said f dash x is equal to, okay, how's our memory? What do we start with? We start with the limit. It's hard to remember, I know. Grab a sheet off the front desk. As h approaches 0. Okay, then you've got your fraction, which corresponds to rise over run, right? Rise over run. So you've got this part here. This is your y2 minus y1, right? Which is just like gradient. And you've got x2 minus x1 on the bottom. Okay? So, this is a really useful way to approach things. However, I want to introduce a different way of saying the same thing because it turns out to be really important in getting one of the results that you're going to use all the time. Okay? Now, just before I start, okay, this proof is not going to necessarily be something that you get tested or anything like that. But you want to know where it comes from so that as you use it, it's not just like some magic whack art. You're like, it works, but I don't know why. So that's why I want you to get this part down. Okay? So before we said you've got 2 points, x and x plus h. Okay? X being some variable that can move around. Okay? So what I want to do here is instead of working out x and it can move around anywhere, I want to work it out at a particular point. And I'm going to call that c. Okay? So I would read that as f dash c, namely the gradient at x equals c. Okay? So therefore, I'm going to introduce some point, c. Let's put it over here. So if that is c, then its height will be, if this is just f of x, what will its height be? F of c. Good. Okay, so far so good. Now, I need to introduce some other point that's going to travel towards c, so that just like before, as we had h approaches 0, we've got it approaching the gradient at a single point, okay? So this time, I'm going to introduce another point. And because I want it to move, I'm going to call it x. Okay, so this corresponds to our x plus h from before. Okay, alright? So therefore, what will its height be? If I come across over here, that's x, so this is f of x. Okay, so now I want to work out this gradient, okay, at this particular point c. It's going to work out in much the same way, except there are going to be minor differences up here. For instance, there's no h. There's no distance here that's approaching 0. Instead, what I want is for this point, x, or rather this point, sorry, to move towards the other point, okay? So I want it to sort of edge its way closer to c. So therefore, instead of h equals 0, I'm going to have x approaching c. Does that make sense? Therefore, in the same way, what have I got over here? This rise over run will also look slightly different, okay? I'm going to have y2 minus y1, right? So y2 minus y1, that's my rise, okay? And in the same way, I've got my run over here, which is x minus c. Okay, so why do we go and use this example? Use this different way of writing it. Okay. Well, number one, sometimes the algebra works out easier when you're doing particular examples, and I'll show you one in a second. And secondly, you remember that result we looked at before when we were proving what we called the rule for polynomials or the rule for differentiating powers, right? We said that this derivative was equal to, do you remember? And you bring the power down, and then you reduce the power by 1. Okay? Now, we sort of proved, we didn't really prove it, did we? We saw it worked in a lot of different ways. We used first principles, but that was kind of just like proving by example. Okay? And proof by example doesn't really work. That's like saying, I can prove that every student at James Bruce is a girl, because I say, look, here's one, here's another one, here's another. So look, all my examples, they're all girls, right? So, proof by example isn't a very good method, right? So if you want to get something more rigorous, we're going to need something better than just coming up with 4 or 5 examples. And it partly depends on this. So let me give you an example of how does this play out. Okay, let's take one that we actually know, so that when we get the result, it'll be something you expect. Let's take f of x equals x squared. Okay, so you already know, just by looking at it, because of this rule, its derivative will be 2x. So if I want its derivative at c, it will be 2c, right? Because x equals c. Okay. So how would I use this? How does the algebra work out a little differently? Well, let's have a go. F dash x equals, okay, sorry, f dash c. I want to add this particular point. Okay. I'm going to take the limit, but this time it's x approaching c. Okay. And then up the top, what have I got? I've got x squared minus c squared over x minus c. Okay, happy so far? Then you can see, all right, my goal here is that I can't simply put in x equals c, right? Because I've got this denominator problem, so I need to get rid of the denominator problem. What should I do? Factorize. So I've got difference of squares, yeah? Okay, happy? So you can see it cancels, and what you're left with is this. Now, again, you need to think about this, okay? Now that I've got rid of my derivatives, I can say, well, sorry, my denominator. Now, as x approaches c, what happens? This will approach c, so I'll have two c's, which is what you're expecting, right? Okay, now that's fairly trivial. In fact, if you look at this example, using the original first principles, the first principles, the algebra is no more difficult, okay? So,